Alright, hello everyone. My name is Ritesh Pandey, and in this video, we'll take up what's called the mole concept. Now, the mole concept is taught much before class 11, and in class 11 physical chemistry, it's presented like the very first topic where we have to deal with the count of atoms, molecules under different conditions. Now, any branch of physical chemistry, any topic of physical chemistry, certainly until and unless the concept regarding the count of particles is fundamentally very strong, the student is going to falter. For some reasons, what otherwise should be a very basic elementary topic of physical chemistry is generally a problem with most of the students. I found places where people are absolutely scared of mole concept, and I think the reason is the fundamentals, the basics are not understood properly. Otherwise, if we deal with this topic, right from the ground state, very fundamentally, chances are it's a topic which is absolute fun and certainly the backbone of everything which we do in physical chemistry in future. Now it's more like a habit. I start mole concept with a problem, a question, and it might look like a very unique kind of question to you. It might not be a real exam problem, but it's a very fundamental question about the term mole. Suppose I ask you a question like one mole defines, and the way in the MCQ paper you have options A, B, C, D. The various options are number of atoms in 12 gram carbon, number of atoms in 12 gram carbon, where you are told the atomic weight of carbon is 12, number of molecules in 32 gram oxygen, where again you are told the molecular weight of oxygen is 32. Suppose number of molecules in 22.4 liters of any gas. It could be hydrogen, it could be nitrogen, it could be carbon dioxide, ammonia, etc. At NTP, 0 degree Celsius, 1 atmosphere pressure, and option D is 1 mole defines a pure number. Now, when I present this question in a classroom, a real classroom, I find people a little confused, because if you know atomic weight, molecular weight, and this is supposed to be the molar volume, and all of this is known before class 11, you start feeling that A, B, C all are right. 1 gram atomic weight, you're dealing with 1 mole of particles. 1 gram molecular weight, you're dealing with 1 mole of molecules. And at NTP, 22.4 liter molar volume is about 1 mole molecules, and all of this is taught before class 11. So naturally a student will start thinking A, B, C all look correct. So many times people are biased towards carbon 12 and they end up giving me a reply like A. Naturally, the right answer, the only correct, the logically most correct answer to this question is option D. It's a pure number. I repeat, it might not be a real exam question, but this will teach you something very fundamental about the mole. The moment I change this question, instead of a mole, the moment I ask people what is 1 dozen, and suppose the options are 12 apples, 12 mangoes, 12 pencils, 12 mangoes, 12 pencils, and here if I put an option like a pure number, when it's about a dozen, 12 apples, 12 mangoes, 12 pencils, and when I put it in form of dozen, more people come up with the answer a pure number. Because a dozen, we are fundamentally told, is a collection of 12 particles. So with dozen, you have a kind of freedom that it's a collection of 12 particles. Any collection of 12 particles will be a dozen. And somewhere in your mind, it has been cemented that when it's mole, you got to think about atoms, molecules, and you get confused over option A, option B, option C. The moment I change the question from mole to dozen, more people are willing to reply D, but with more, very few people, come up with option D. Now, first and foremost, mole is a collection of particles. Mole is a collection of particles, and this is also a number which is popularly called Avogadro number. A number which is popularly called Avogadro number. You know, when I say a dozen means a pure number, it doesn't mean that ABC are wrong. It doesn't mean that ABC are wrong. You know, 12 apples, 12 mangoes, 12 pencils are not incorrect options. But the most correct option is option D, because eventually a dozen is a collection of 12 particles. So it doesn't mean that A, B, C are wrong, but D is fundamentally correct, the most correct answer. Again, this might not be a real exam question, and A and B and C, we might be talking about the same quantity of particles, the same number of particles. But eventually, 1 mole is a collection of these many particles. 6.023 to 10 to the power 23, a number with all of you are familiar with, is called the Avogadro number, represented with a capital A and a capital N and a capital A in the subscript. You know, we call it the Avogadro number. An interesting fact being, although it's called the Avogadro number, this number was not given by Avogadro, because Avogadro's hypothesis was very early in the beginning of 19th century. Avogadro came with the concept of molecules, and the hypothesis was equal volume containing the same number of particles, which we now call molecules. It was a hypothesis. This number came much after Avogadro's hypothesis. This number came almost 30 to 40 years after Avogadro's hypothesis. You know, with respect to this great scientist, we call it Avogadro number, but an incidental fact is Avogadro number was not given by Avogadro. And it's a huge number. 6.023 to 10 to the power 23 is a huge number. 6.023 to 10 to the power 23 is a huge number. It's a number which is practically impossible to deal with. It's a number for which only atomic, subatomic particles and the count of atomic, subatomic particles is relevant, and it's more like a habit. We grow up in this manner. In the field of chemistry, we grow up assuming that every time it's mole, it has to deal with number of atoms and molecules. But trust me, this is very much like a dozen, which is a collection of 12 particles, or a score, which is a collection of 20 particles. So first and foremost, 1 mole is a collection of these many particles. When I was in class 11, Sanjeevi's Kolkata, a very popular book of chemistry titled Elements of Chemistry, although it's no longer in publication, but if you look for the old edition of this textbook, Elements of Chemistry, Volume 1, Elements of Chemistry, written by Dr. Ganguly, who happened to be our HOD in St. James, Calcutta. So Maiti Ganguly were the two authors of that book. And in that particular book, Elements of Chemistry, Chapter 1, Mole Concept, I recall, towards the end of the chapter, there was a statement, 1 mole of pencil means these many pencils. 1 mole of pencil means these many pencils. So the idea was very clear that 1 mole is basically a collection of particles. It's a number. Literally means, it means a heap, a collection. And like a dozen, it's also a pure number. Because it's a very big number, we end up using it only for the count of atomic, subatomic particles. But you also should know that 1 mole is basically a pure number, which is called the Avogadro's number. 1 mole of pencils might mean these many pencils. I'm going to write another question. Now this time it's a real exam question. It came in the IIT way back. I believe in the 80s, early 80s, there was a question like this in one of the IIT papers, chemistry. And you're going to enjoy this question. So you'll want to maybe copy this at your convenience. And although A, B, C are not wrong, 1 mole is basically a collection of these many particles only. Now I'm going to write a question which is a real exam problem. Told you, it came way back in the early 80s in the IIT JEE question paper. And again a very unique kind of question, The question reads, spending money at the rate of 1 million per second, which is 10 to the power 6 rupee, 1 million per second. Spending at the rate of 1 million per second. Find number of years taken. to spend 1 mole rupee, to spend 1 mole rupee, to spend 1 mole rupee, 1 mole rupee. God knows why this was there in the physical chemistry or the chemistry paper of an ITJ exam. But when I'll be solving it for you, you would again realize that this is going to have a very fundamental meaning, a very fundamental objective. Like, it's basically a problem of simple mathematics, simple arithmetic. First of all, it's again impractical. Per second, like every second ticking in the clock, you have to spend 1 million rupee. 1 million per second would mean 6 crore of rupees per minute. Maybe the problem was framed in terms of currency because it's human nature. Large big number, it's easier to think in terms of money. If I tell you 1 million, you will naturally mean 1 million rupee. You will not consider 1 million chewing gums. So 1 million, 1 crore, 6 crore, 1 million per second is impossible to spend. 1 million per second, 10 lakhs per second, and in 1 minute, you spend 6 crore rupees. 1 hour, I believe it's more than 350 crores, 360 crores to be precise. And 1 day, 24 hours, it's more than 7,000 crores. Again, next day you have to spend more than 7,000 crores. Day in and out. With the clock, seconds ticking in the clock, every second 1 million is practically impossible to spend. But hypothetically, if you are given 1 million rupee, and you have to spend it at this impractical rate, how many years will it take? Simple problem of arithmetic. The total money is 6.023 into 10 to the power 23. This is the total amount of money. And you have to spend this much per second, per minute, per hour, per day, per year. Simple. This is spent per second into 60 per minute into 60 per hour. 1 day has 24 hours and a normal year 365 days a year. This is the money spent per year. This is the money spent per year. This is the total amount of money. So this will give you number of years. And if you go about solving it, the value would be staggering. Spending at this impractical rate of 1 million per second, the number of years taken would be 1.9 into 10 to the power 10 years. 1.9 into 10 to the power 10 years. Trust me, it was a real exam question, came in the ITJ way back. And 10 to the power 10 years is 10,000 million years. 10,000 million years. This is comparable to the age of a planet. Certainly human civilization will not live this long. 10 to the power 10 years is comparable to the age of the planet. God knows whether the solar system will survive this long or not. So when we are looking at spending 1 more rupee at an impractical rate, the number of years taken is 10,000 million years. Certainly human civilization will not last this long, and the learnings from this problem could be, you can never even imagine spending this much of money or printing this much of money. You can't even deal with such huge amount in terms of currency or money. This being a real exam problem, any day when you solve it and realize it's going to take 10 to the power 10 years, you would understand how big this number is, So if you have to, make 1 million pencils, going back to that statement from the textbook, if you have to make 1 million pencils, and suppose all the people in this planet, all the factories and all machineries are deployed to make pencils only at the rate of 1 million pencils per second. Certainly to prepare 1 million pencils per second, you will need more trees than there are on this planet. These many pencils cannot be practically prepared out of the wood, which is there on the planet. But suppose you are able to do that, make 1 million pencils per second. Number of years taken to prepare 1 mole of pencils is 1.9 into 10 to the power 10 years. So, in terms of money, in terms of practical objects around, this is a very big number. It's a very big number. And if you want to get, more acquainted with some amazing facts about this number, it would take a lot of time, even writing 23 zeros after 1. What you can do is, you can Google fun facts about mole, fun facts about mole, fun facts about mole. You will want to add chemistry here, because mole is also the name of an animal, a rodent. If you Google fun facts about mole, you will find several pages, with some mathematical data or the other. Like this I call as a fun fact. Maybe it came in an exam only to teach people how big this number is, but eventually it's a fun fact. Now when you Google fun facts about mole, a lot of data. I can share a couple with you right now. Suppose you are given 1 mole of coins. Yet again, 1 million of coins cannot be printed, 1 million of coins cannot be made, because if you go about making 1 million coins per second, 1 million coins per second, the number of years taken to prepare 1 million coin, 1 mole coins will be 1.9 into 10 to the power 10 years. But suppose you are given 1 mole of coins, the normal rupee coin which I have, and you're piling it up. You're preparing a tower of, you're piling it up on top of each other. You're piling it up. 1 mole coin starting from the planet Earth. It's again going to be a problem of mathematics, because every coin will have its thickness in millimeters. That millimeters into 10 to the power 23 would be in kilometers, and then it would go into light years. If you are given 1 mole of coins and you stock it over making a tower, you pile it up, how high that tower is going to rise. The tower of 1 million coins, the distance, the height would be in light years. It takes a little more than 8 minutes for light to travel the distance between Earth and Sun. So naturally, this 1 mole coin Qatar will go past the Sun, will go past the solar system. You can have several trips of the Earth and Sun with this distance. It's going to go beyond the solar system. A very staggering fact, I read somewhere in the recent past was 10 to the power 23 is such a big number, and this was really very astonishing. 10 to the power 23 is such a big number that 1 mole of rice grains have not been cultivated on this planet. It's said that the oldest culture is agriculture. And imagine, from the beginning of time, a rough data says that 10 to the power 23 rice grains have not grown, have not been cultivated on this planet. Talking about human beings, if the entire population starts counting at the humanly rate, if the entire population of the planet starts counting at the humanly rate, 1 mole cannot be counted. 1 mole cannot be counted by the entire population of the planet in their average human life. It would take millions of years for supercomputers to count 1 mole particles. Human cells, we are made up of 60 trillion cells. Cell is supposed to be the smallest unit of life. In biology, cell is supposed to be the smallest unit of life. We are made up of 60 trillion cells. And the living human cells of the entire living population, the total number of living human cells on this planet is barely half a mole. Even that is not equal to 1 mole. So you realize 10 to the power 23 is like an astronomical figure. It's comparable to the number of water drops in an ocean, or it's comparable to the number of sand grains on a sea beach, which is kind of impossible to count. And the more you know about how big this number is, the more you realize how small an atom is. Because a number which is beyond count, beyond imagination, impossible to deal with, and these many particles are there only in 1 gram of hydrogen. Only in 1 gram of hydrogen, you have a number of atoms which is beyond count, which is beyond imagination. So certainly, the more you learn about how big this number is, you realize how small an atom is, And when you realize how small an atom is, an atom cannot be directly weighed. an atom cannot be directly weighed. I found people committing mistake like one atom of hydrogen is 1 gram. That is impossible that's an impossible mistake to commit. An atom is like infinitely small. So atom cannot be directly weighed. And when atoms cannot be directly weighed, how do you find the weight, atomic weight, molecular weight? I'll give you an analogy again. Suppose you have a pool of dirty water. You have a pool of water or a sample containing several microorganisms, bacteria, fungi and all. Now naturally you can't see the microorganisms by naked eye, by human eye. You use a microscope. To see different types of bacteria, different type of microorganisms. You use a very sophisticated microscope. Now something which cannot be seen by human eye, you're barely viewing it using a microscope. You can't measure them in measuring tapes. You can't measure them in units like millimeters or centimeters. So how would you measure those particles to begin with? What you can do is, when you find several bacteria of different size and dimensions, you can choose the smallest one. You can identify the smallest one, and then you can say that, alright, this is the smallest one, the next one is 2 times bigger than it, the other one is 5 times bigger than it, another one is 12 times bigger than it, and now you have a benchmark of kind of measuring all of them by taking the smallest one as the standard. Exactly the same is followed in physical chemistry mole concept. You take the lightest element, hydrogen, as the standard. You take the lightest element, hydrogen, as the standard. And most of you by now know that atomic weight or molecular weight is a ratio. Atomic weight or molecular weight is a ratio. It's a number which tells you how many times an atom or molecule is heavier than an atom of hydrogen. How many times an atom or molecule is heavier than an atom of hydrogen. So, as I told you, it would be an impossible mistake to commit at this level if you believe that atomic weight is the weight of one atom or molecular weight is the weight of one molecule. That would be absolutely unpardonable. So basically, what is atomic weight? What is atomic weight? What is atomic weight? It's the weight of one atom of the element. It's the weight of one atom of the element. Weight of one atom of the element upon the weight of one atom of hydrogen. Upon the weight of one atom of hydrogen. So it's a number, it's a ratio which tells you how many times an atom is heavier than an atom of hydrogen, how many times an atom is heavier than an atom of hydrogen, or these are the other scales. Weight of one atom of element, upon 1/16 of the weight of one atom of oxygen, and naturally you are told that carbon scale is the most relevant one. Relevant means if you write in terms of carbon scale, you get marks in your school exams. So basically, upon 1/12 of the weight of one atom of carbon. Now you began with one atom of hydrogen, and this is the basic benchmark. You call it hydrogen scale, you call it oxygen scale, you call it carbon scale. You're taught that carbon scale is the most relevant one. But basically these values are almost equal. When you learned that oxygen is 16 times heavier than hydrogen, when you learned that every atom of oxygen is 16 times heavier than hydrogen, you realize whether you compare with one atom of hydrogen or 1/16 of the weight of one atom of oxygen, it's the same value. Similarly, you know that carbon is 12 times heavier than hydrogen. The atomic weight of carbon is 12. So every atom of carbon is 12 times heavier than an atom of hydrogen. So naturally, you compare with one atom of hydrogen ka weight or 1/12 of the weight of one carbon atom, you'll get the same value, the same ratio. It all began with taking the atom of hydrogen as the standard. I can again give you an analogy. Suppose you have to measure the length of a room. Measuring length very precisely could also be an experiment. So suppose you are asked to measure the length of a room, a classroom, and you're given two rulers. You're given two rulers, a smaller one and a bigger one. Again, these are questions which I kind of put up in the real class while interacting with the students for the very first time in maybe class 1 of class 11 physical chemistry mole concept. And given a choice, most students opt for the longer scale. Most students opt for the longer scale with the excuse that it's going to take lesser time, it's going to be hassle free, it's going to be easier using with the longer scale. And some intelligent mind would tell me that with the longer scale, the number of operations will be less. And lesser the number of operations, lesser are the chances of error. You would be told while measuring anything, as I told you, measuring length is also an experiment. You will be told, or some of you might know, that measuring anything, there are two types of error. One is the instrument error, experimental error, and there is human error. Now with a longer scale, maybe the operations will be less and the errors will be less. With a smaller scale, because you will need more operations, the error will get multiplied. More number of operations will mean more error. So you opt for a longer scale. Ideally, you will want a long measuring tape and you will want to measure it at 1 mole. That is exactly why from hydrogen we went to oxygen and then we went to carbon, which were heavier references. If you do a small mistake here with the lightest element, the small mistake will get magnified. Like with a smaller scale, any error in the making of that scale will get multiplied. So you move to heavier references, but 1/16th of the weight of 1 atom of oxygen or 1/12th of the weight of 1 atom of carbon is basically the same as the weight of 1 atom of hydrogen. Same for molecular weight. The only difference is, instead of weight of 1 atom of element, you will want to write weight of 1 molecule. Weight of 1 molecule of the element or compound. Weight of 1 molecule of the element or compound. So this ratio tells you the molecular weight. Atomic weight is never the weight of 1 atom. Molecular weight is never the weight of 1 molecule. Never do that mistake ever in your life. Certainly not at this level when you take up science in class 11. Carbon atomic number 12 means 1 atom of carbon is 12 times heavier than 1 atom of hydrogen. Sodium atomic weight 23 means 1 atom of sodium is 23 times heavier than this or this or this. Molecular weight of carbon dioxide is 44 means 1 molecule of carbon dioxide is 44 times heavier than this or this or this. You can have a unit which is called atomic mass unit, AMU. You can have a unit which is called atomic mass unit, which is basically the weight of 1 atom of hydrogen. At some point you will be told that 1 gram atom, 1 gram molecule, 1 gram atom, 1 gram hydrogen is basically going to mean Avogadro number of atoms. So 1 atom would be 1 upon Na grams. This is 1 upon Avogadro number, which is almost equal to 1.66 into 10 to the power minus 24 grams. And is called AMU. Again, 10 to the power minus 24 grams is a very small value. You go very small calculation, but 10 to the power minus 24 is very small and it's a reference. This would be called atomic mass unit. We'll come to it when the time is right. So you can say 1 molecule of carbon dioxide is 44 AMU, which is 44 times heavier than this, or this or this. But it never means that 1 molecule is 44 grams. There are more things which we are trying to learn in a very fundamental manner. Like, what if I write the atomic weight or molecular weight in grams? What if I write the atomic weight or molecular weight in grams? What if I write the atomic weight or molecular weight in grams? Now, when I write it in grams, I call it the gram atomic weight, the gram molecular weight. So, I would stick to the example which I gave you, gram atomic weight of, suppose, sodium is 23. What does it tell you? It tells you a few things. One, every atom of sodium, one atom of sodium is 23 times 1 AMU. Now, what is 1 AMU? weight of one atom of hydrogen, one atom of hydrogen, or 1/16th of the weight of one atom of oxygen, or 1/12th of the weight of one atom of carbon. This is AMU. So it's 23 times heavier than this or this or this. So you can say it's 23 AMU. You can say it's 23 AMU, which is the reference. What it also means is 23 grams of sodium will contain Avogadro number of atoms. It will contain Avogadro number of atoms. So 23 grams of sodium will contain Na atoms. Very rarely I am going to write this whole number. I'll prefer using Na most of the times. Similarly, gram molecular weight. Suppose carbon dioxide is 44. Never means one molecule is 44 grams. It means that one molecule of carbon dioxide. You know how to get the molecular weight conventionally? 12 plus 16 plus 16. So 32 plus 12 is 44. So one molecule of carbon dioxide is 44 times heavier than any of these. It also means that 44 grams of carbon dioxide will contain Na molecules. Will contain 1 mole of molecules. So basically atomic weight in grams is the weight of 1 mole of atoms, and atomic weight in molecular weight in grams is the weight of 1 mole of molecules. Na molecules. It's about weight in grams. When it's gaseous, volume, naturally, you will want to keep copying this at your convenience. When it's gaseous, volume, and naturally, we'll go back to Avogadro's hypothesis. Now, Avogadro's hypothesis in the beginning of 19th century, almost 200 years back, Avogadro's hypothesis said equal volume of all gases under the same conditions of temperature and pressure will have same number of molecules. One way of keeping them at same pressure and temperature is to keep them in the same room. So if you keep all of them in the same room, be it hydrogen or oxygen or nitrogen or ammonia, different smell, different color, different density, but if their volumes are equal, and they're all kept in the same room, so when you keep them in the same room, naturally they are under constant pressure and temperature. Equal volume at the same condition of pressure and temperature will have the same number of molecules. And the reverse of this hypothesis could be, certainly we know it's a correct hypothesis. The reverse of this hypothesis could be equal number of molecules. The reverse of the same would be equal number of molecules under the same conditions of pressure and temperature will occupy the same volume. And in gaseous state we can prove that Na particles, atoms if it's an elemental gas like an inert gas, or molecules more often than not at NTP will occupy 22.4 liters. This is popularly referred as the molar volume. So 22.4 liters is the volume of Na molecules. It could be Na molecules of oxygen, nitrogen, ammonia or any gas. Equal volume containing the same number of molecules. The reverse could be same number of molecules will occupy the same volume. And it's called the molar volume. 1 mole of molecules, Avogadro number of molecules at NTP for all gases will occupy 22.4 liters or 22400 ml. So you've got some benchmarks now, we have got some benchmarks now, and trust me, all of this is taught much before class 11. This is nothing new. I'm not going to try you things, which are like very sophisticated or absolutely new. Things which you have been taught in the past, now you want to apply the same very fundamentally with a lot of care. So now, if you know that 22.4 liters will mean these many molecules, you have an idea of finding number of atoms and molecules. You have an idea of calculating number of atoms and molecules. You have an idea of calculating the number of atoms and molecules. Every time you have weight in grams, every time you have weight in grams, you will want to divide it by you will want to divide it with atomic weight. Every time you have weight in grams, you will want to divide it with the atomic weight, and this will be number of moles of atoms. Certainly, if you divide it with the molecular weight, it will give you number of moles of molecules. And if you have a volume, again, if you have a volume in liters at NTP, then you will want to divide it by 22.4, and this will give you the number of moles of atoms or molecules, depending whether the gas is elemental, inert gas, or a molecular gas. So, atomic weight in grams, gram atomic weight is 1 mole of atoms. So weight upon atomic weight is the number of moles of atoms. This in grams is the weight of 1 mole of molecules. So total weight upon molecular weight is the number of moles of molecules. I'll quickly give you an example. You have 64 grams of oxygen. 64 grams of oxygen. When you divide 64 by 16, you get 4 Na atoms. And when you divide 64 by 32, which is the molecular weight, you get 2 Na molecules. So this is 2 moles of molecules. 64 grams is 2 moles of molecules. You also know O2 is diatomic, so 1 molecule into 2 is the number of atoms. But when you divide with atomic weight, you get the number of moles of atoms. When you divide with molecular weight, you get the number of moles of molecules. It's always safe and correct to calculate in terms of moles, Now what about volume? If you are given a problem in volume, so you will want to keep these in mind. Every time weight is given, divide with atomic weight or molecular weight to give you number of moles of particles. Every time volume is given, you will want to divide with 22.4 to find the number of moles of molecules, and then you can take on from that point. I'll also tell you in this video how to find number of individual atoms if it's a heteroatomic molecule. Heteroatomic means containing different atoms. Oxygen, nitrogen, chlorine are homoatomic, made up of only one type of element. But ammonia, carbon dioxide, methane, they could be made up of different type of elements. They are called heteroatomic molecules. So I'll also tell you how to calculate the number of atoms in heteroatomic molecules. And suppose again we are given a problem like 1.6 gram methane. You need to know the molecular weight of methane is 16. Now weight upon molecular weight. This is 0.1 moles. This is 0.1 moles. So this is 0.1 Na molecules. Because you are dividing by molecular weight, it's 0.1 Na molecules of methane. Now how do you find individual atoms? One methane contains 1 carbon and 4 hydrogen. One molecule of methane contains 1 carbon and 4 hydrogen. So these many molecules into 1 would mean 0.1 Na atoms of carbon, and into 4 would mean 0.4 Na atoms of hydrogen. I repeat, one molecule contains 1 atom of carbon, 5 molecules will contain 5 atoms of carbon, 10 molecules will contain 10 atoms of carbon, and so and so. So these many molecules, you always deal in number of moles. You find number of moles, 0.1 mole means 0.1 Avogadro number of molecules. Because mole is the count of these many particles. One molecule contains 1 carbon, so the number of molecules is equal to the number of atoms. Every time you have to calculate it, you can always count 0.1 into 6 into 10 to the power 23. Almost 6 into 10 to the power 22. I am avoiding writing 0.023 every time. And 4 times of this will be the number of atoms of hydrogen. 4 times of this will be the number of atoms of hydrogen. So you can always do this, you can always do this. You can always do this for carbon hydrogen, you can always do this for other cases involving ammonia or other heteroatomic molecules. You will want to copy this at your convenience. And suppose once you have copied it, we take up a couple of more cases. In volume, 11.2 liters of ammonia, 11.2 liters of ammonia. Now right away you will want to divide this volume with 22.4. When you divide it with 22.4, it's half moles. Now it's half moles of molecules, half Na molecules, half Na molecules of ammonia. Yet again, one molecule contains 1 atom of nitrogen, one molecule contains 1 atom of nitrogen. So 1 contains 1, half Na molecules will contain half Na atoms of nitrogen into 3 1.5 Na atoms of hydrogen. You want to copy this at your convenience. You want to copy this at your convenience. So, even if it's a heteroatomic molecule, containing 2 or more types of atoms in a molecule, this is how we approach it. Simple as it looks. Ammonia, one molecule contains 1 atom of nitrogen. One molecule contains 1 atom of nitrogen. So 5 molecules will contain 5 atoms of nitrogen. One molecule contains 3 atoms of hydrogen. So 5 molecules will contain 5 into 3, 15 atoms of hydrogen. So from number of molecules into 1 is number of atoms of nitrogen, into 3 is number of atoms of hydrogen. So basically, if we can begin on the right note, if we can begin with the number of moles right away, everything else will fall into place. Everything else will fall into place. 0.5 Na will be 0.5 into 6.023 into 10 to the power 23. 1.5 times of this, we can always calculate these numbers. Otherwise, it's best to carry on with Na. It's always good to carry on with Na. Suppose you are given 3 moles of phosphoric acid. You are given 3 moles of phosphoric acid. Now, when you are given 3 moles of phosphoric acid, then it's simpler. 3 moles of phosphoric acid is simple. Already given the number of moles. From the weight or volume, we have been finding number of moles only. Here the number of moles is already given. So when it's number of moles to begin with, even simpler. 3 moles of phosphoric acid will mean 3 Na molecules. 3 Na molecules of H3PO4, and I think by now you have got a hang of it. 3 Na molecules means per molecule 3 into 3, so 3 into 3, 9 Na atoms of hydrogen into 1, this is 3 Na atoms of phosphorus, and into 4, this will be 12 Na atoms of oxygen. So what I have tried to do in this class is, always obtain number of moles in the beginning, and with number of moles and then the number of molecules, individual atoms can be calculated as simple as I have done here. Yet again, 10 molecules of phosphoric acid will mean 30 atoms of hydrogen, 10 atoms of phosphorus, and 40 atoms of oxygen. So number of molecules into 3 is for hydrogen atoms, into 1 is for phosphorus atoms, into 4 is for oxygen atoms. In the upcoming videos, I would be solving too many questions. But before that, you need to do it at your end. You need to be very comfortable dealing with number of atoms and molecules, because there is a variety of the type of questions which can come in the MCQs form or other forms, and in all of them you need to begin with the number of moles. Dealing in number of moles will make the topic easier. If you are watching this video before class 11, it depends how your school teacher tells you. If they're happy with Na, you'll want to deal with Na. Otherwise, you'll say 9 moles of atoms. So, this much I guess in this video. Keep trying, keep solving more questions of this type. And in the upcoming videos, chances are we'll be dealing with more numerical problems of this kind. Thank you so much.